So, how do heavy machines, and more importantly, the human operators inside them, actually survive the deadly, freezing reality of the world's deepest winters? Well, today in this explainer, we're going to dive into a fascinating piece of engineering that acts as true Arctic life support.
Just imagine for a second being part of a Siberian winter military convoy. The temperature completely plummets to minus 50 degrees Celsius. At those extremes, the cold isn't just weather anymore. It's a severe operational constraint. It is a visceral, incredibly dangerous cold that turns every single piece of steel on your vehicle into a literal weapon against you. You're basically sitting inside a giant metal box that actively wants to pull the heat right out of your body.
Section 1. The engine heat myth. Idling isn't enough.
You'd probably naturally assume that the massive diesel engine roaring away in your truck is all you really need to stay warm, right? But reality quickly shatters that myth. In extreme Arctic conditions, idling a huge engine for 10 hours just to keep the cabin slightly tepid, it's incredibly inefficient, not to mention impractical. Moving air circulates freely in the cargo bed, and within minutes, that uninsulated metal compartment just completely matches the deadly outside temperature. After just a few hours, you aren't just uncomfortable, the cold is actively robbing you of the manual dexterity and the mental concentration you literally need to do your job.
Section 2. The autonomous furnace. Independent heating.
So, to solve this, Soviet engineers came up with an absolutely brilliant solution to keep soldiers from freezing to death in vehicles like the ZIL or KAMAZ trucks. And the crucial thing here, they didn't rely on the truck's main engine at all. Instead, they built a completely independent autonomous furnace, like the famous OV95. It's a fully separate system that runs on the exact same standard diesel fuel as the truck, but it can operate flawlessly even when the main engine is dead silent. Now, if you've ever seen these trucks, you might have noticed a strange vertical metal unit bolted to the back of the cab, unconventionally mounted outside, sometimes even sticking right up above the roofline between the cab and the cargo bed. It looks kind of odd at first glance, but in a world of minus 50 degrees, aesthetics really do not matter. Simplicity and independence absolutely do. Mounting it externally meant soldiers could easily access and service the unit right there in the field, without having to tear the truck apart in freezing temperatures.
Section 3. Safe air separation. Isolating exhaust.
But that brings up a really big question. How do you run a diesel furnace right next to a cabin without filling the troop compartment with deadly exhaust fumes? Well, the answer lies in a highly specialized life support heat exchanger. Basically, outside air enters the unit and goes into a combustion chamber where a diesel burner creates a stable fire. Now, that fire is kept in a totally isolated enclosure. The air you're actually going to breathe passes through entirely separate internal channels. It's a beautifully clean, safe separation of flows. The breathing air simply soaks up the heat through the metal walls, and it never ever comes into contact with the toxic exhaust gases.
Section 4. The bottom-up heating strategy for uniform distribution. Alright, so once that air is safely warmed up, the next big challenge is figuring out exactly where to route it inside a freezing metal box. Engineers chose to deliberately feed the warm air directly to the floor level, and they did this for a very specific reason. The vast majority of heat loss in these trucks happens right through the metal floor and the lower side panels. By pushing the heat from the bottom up to counteract that loss, they successfully created a uniform temperature distribution. The warm air naturally rises and simply displaces the freezing layers of air above it. Makes sense, right?
To put that into perspective, look at the sheer power of this system on this chart. It's just incredible. In trucks like the GAZ-66 or the ZIL 131, this furnace could take a punishing minus 35-degree night outside and literally turn the inside of that metal truck into a highly survivable, remarkably comfortable plus 15 degrees Celsius. Now sure, a plus 15-degree cargo bed isn't exactly a luxury hotel experience, but it absolutely succeeded in its primary goal. It completely preserved the mobility and, more importantly, the operational readiness of the people trapped inside. It ensured they could survive the grueling night and still have the vital physical dexterity to actually perform their duties the next day.
Section 5. The Simplicity Survival Rule. Reliability first.
This incredible mechanical ingenuity reveals a much broader, overarching engineering philosophy when it comes to extreme survival. By prioritizing rugged mechanical simplicity and autonomy over fragile, complex electronics, these machines operated flawlessly in conditions that would instantly brick a modern vehicle's computerized systems. It is the ultimate proof that in the most extreme environments on Earth, the best engineering isn't always the most complex, it's the most reliable.
Actually, it's so reliable that these exact types of autonomous heaters evolved directly into the compact, quiet units that are widely used in modern motorhomes and long-haul trucks today.
The Arctic life support logic remains exactly the same today as it was back then. Heat the person, not just the machine. I'll say that again. Heat the person, not just the machine. That straightforward logic is exactly why modern vehicles still rely on this evolved technology. Because when the thermometer bottoms out, you simply have to prioritize human survival above all else.
These systems remind us of a profound truth. In the world's most hostile environments, survival doesn't depend on microchips or digital screens. It depends on rugged, unyielding simplicity. If an autonomous metal furnace is what stands between life and death at minus 50 degrees, it really forces you to wonder, as our modern world becomes increasingly fragile and digitized, are we actually engineering ourselves away from true resilience? So have you ever had to operate a machine in extreme sub-zero temperatures? If so, how did you keep from freezing? Think about it.